What thing? Oh, oh no, he cannot. He's gonna eat it. Yeah, he likes this little thingy. Hello everyone, it's February 27th. Well, yesterday was the contest. Did so. I mean, was it tough? The last question was tough because I didn't do it. I wasn't able to figure it out. The first three was okay. It was not too bad. What should I say? Let's see what's the ranking. I think I didn't rank very well because I didn't do the last one. The last one still need time. I probably have to read the solution. Wow, 9 minutes, the top one. 2,000. The ranking is 2,000. Yeah, that's bad. Well, for one thing, I didn't start at 15 minutes. Alright, so I think I started late. So that's another reason. But the good thing is I didn't have any wrong. So that's a good thing. But the last question was just tough. It's right here. Right here. Minimum finish time. I was able to get to TLE, which means the logic was correct. It was just too slow. But still, that's not good enough. Yeah. So we'll figure it out. So I didn't do LeetCode yesterday, which means I have to use a time travel today to do this, and I have to do another one later. But the another one will be an easy question, so don't worry about it. All right, so this is for yesterday. Maximum width of a binary tree. I think I've done this before. Yeah, July the 9th, 2020. Okay, so maximum width. So given the root, return the maximum width is the maximum width among all levels. The width of one level is defined as the length between the end nodes, the leftmost and the rightmost non-null nodes, where the null nodes between the end nodes are also counted into the length. Oh, that's what is hard. Well, I shouldn't say hard, that's what is tricky. The answer is okay, so it's 1, 2, 3, 4. Got it. This will be 1, 2. Okay. So at this level, oh, it has to be between. Okay, it has to be between. Anything between. There shall also be 2, because there's nothing in between. Alright? So I want to find the maximum width from the root, right? Which is not, technically is not the maximum width of left and right. Because if I say, okay, the maximum width of this is the maximum of left plus the maximum of right, then the maximum of left is 2, maximum of right, that's 0, right? And that's 1. This one is 1. So this one returns 3, because this one does not count. But in effect, this one has to count. Okay. Interesting problem. And what do we do? Well, in this case, right, see the left has some, but I don't know if it's like the leftmost, right? This is the decision I have to make for each root. I have a left and right, right? And I know they will branch out. So the question is, what is the leftmost on this? Now, what is the rightmost on this, right? And the levels, okay? So maybe we need to find the level as well, because this is one level, this is a one level, right? So I say Now, from this perspective, so this tree returns, yeah, all I want more leftmost. If it's like a tree like this, and this, like if I extend to 4, and then I go inside, right? Then the leftmost. So we want to find the leftmost. It has to be on the same level. It has to be on the same level. Well, we just try to find each level, right? So at each level, we find the leftmost and the rightmost. But how do we know the leftmost and the rightmost? Huh. The leftmost. Yeah, it's like if I don't have this 5, the leftmost is 3 on this level. The leftmost on this level will be 3, right? Will be this one. Well, if we do BFS, right, then we have all the nodes on each level. So we have the leftmost node and the rightmost node. We do have them. Now the question is just how many more in between, right? That's the problem. Can we assign index to them? If I assign index to them, maybe. Well, let's think about it. If this is a 0, 1, 2, right? And then this one will be times 2. Is times 2 plus 1. So 1, 2, 0, 1, 2, 3, 4. Wait, hold on. I remember 1 index and 0 index is different. Hold on, let me see. I forgot. 0, 1, 2, 3, 4, 5, 6. And then 0, 1, 2 times 2 plus 1. Times 2 plus 1 times 2 plus 1. Maybe 1 index is easier, right? 1, 2, 3, 4, 5, 6, 7. Yeah, 1 index. I remember I like 1 index. 1 index, the left node is times 2, right node is times 2 plus 1. So what I do is I will mark their indices, right? For BFS, for each row, each level, I mark the indice when I push into the queue. Therefore, I know the index of the leftmost, I know the index of the rightmost, and the number is just the difference of the two. Yep. Let's do this. You see, I'm trying to solve another problem here. That's just for some interesting experiment. What the hell is this? All right. Ooh, I didn't. Let's say complete contest. That's 220, 282. All right, let's do today. Now that's not today. I was supposed to do this yesterday, but that's fine. 7. So when I use BFS, all right. So Q equals to when I have the root and index, right? I have this, and then the rest will equal to. I want to find the maximum width, so we go with 0. Actually, not 0. We'll go with 1. And while Q, right? While Q, temp is this for node index in Q, right? And then we say, actually no, we should first compute the maximum. So we say rest equals to max. Oh, hold a sec. Number of nodes is 1 to 3,000. Okay, so 1 is fine. So it would be the maximum res and q minus 1, 1 minus q 0, 1 plus 1. Right, that will be the difference because, yeah, indices. Yeah, so that will be res, and then now we say if node dot left, go left first, temp dot append. Now when we append is two things, right? So when you append node dot left and index times 2. If node dot right, temp dot append node dot right and index times 2 plus 1. Okay, so blah blah blah. Once we're done, q equals temp blah blah, return res. Okay, we're not going to test this because it's tree, and usually don't test trees because it's too hard to write a test case. So let's just go ahead, do this, and of course let's do a single test case. Well, I just realized I can do res equal to 0. It doesn't matter. Yeah, I let it's equal to 0. I like to be equal to 0. All right. You want some other? No, I think this is correct. What is this? Oh, there's notes. Ha! I have no clue. I don't need it. I just submit this. All right. This daily challenge, there are 2 incomplete challenges, and you have 1 ticket left for this month. Are you sure you want to use a ticket and make up this? Yes, I want. And this is for yesterday. Let's do this. I'll make it for this. Okay. All right. So that's that. I did pretty well. I got a 99% ranking. So, what is this? 662, right? BFS with indices, right? Indices for each node. It's ON. $44. 90%. No, I thought it was 99. It's not 99. It's only 90. All right. So take a look at the solution I had in the past. So it's good, then it shall be good. Oh, I was using the deck back then. Why do I keep tracking of the level? I have no clue. I don't understand. It looks terrible. Stupid code. I don't like it. Yeah, the level is irrelevant. Right? The level is irrelevant. Look at this. How nice. Nice and neat. Okay, so that will be it. That's the makeup for yesterday. I want to continue by solving this one. Alright, so we're gonna ignore this for now and try to finish on this one. So this is LFU, the least frequently used cache. And I was about halfway through. Wow, it's raining. Alright, so the ideal is, it's a cache, right? So every time you input data into this cache, it will check if the capacity has been reached. If the capacity has not been reached, we just put it in, it's fine. If capacity has been reached, then you need to pop something out. And in this one, the rule is you pop the one with least frequently used. So we have the frequency counter for each node, and when you pop the one with the least frequent. And in addition to that, if the node is least, if the frequency is the same, right? You have multiple nodes with least frequently used, then you shall pop the least recently used. So you need to keep another variable to check the tick. Well, basically just the time, right? The timestamp. I did the least LRU cache, the least recently used cache, and it was very smart using a doubly linked list to achieve everything in ON. I shouldn't say ON, it's actually O1, right? So for the get and put is all in O1. But in this one, I figure it's a hard problem, so probably it's a different solution. So I would just go for the heap queue, right? We go for the heap queue. And I'll define the node myself, which I'll define the dunder LT less than function. So I use this function to tell the heap how to compare between the nodes. So what I say is the frequency is the same, then I'll check the tick, right? The tick with smaller will go higher. Oh, hold on. Yes, the tick smaller go higher, so go to the front of the queue, because the smaller tick means it's the last time it used is in the past, right? So the larger the tick, the more recent it is. The smaller the tick, the least recent it is. So this means if I have the same frequency of using, then the one it recently used will pop to the front of the queue. And if the frequency is not, the same, then of course we get the smaller frequency to the front. So this will guarantee the front, the top of the queue, always has either the smallest frequency, or if the frequency has multiple smallest frequency, it has the earliest used, so the least recently used. So that was the node, and I was doing the put, right? The put. Okay, so every time we do put or get, and actually I can do on get as well, because these operations always implement the tick, right? These operations always implement a tick. Tick just means, just keep ticking. Time keep ticking forward. So everything can call it, they have the new tick. And whatever the nodes that's involved in these operations will get the new tick. That's the basic idea. So I say if length self.heap, I have a heap which is just a list. If it's smaller than the capacity, right? If it's smaller than the capacity, that means we can add a new one. So I create a new node with key value, and the tick is self.tick, the current tick, which is correct. And then I'm going to add this into the queue, which I will do. And of course, the default value for frequency is always 1, right? The default value for frequency is always 1. So in this case, I'm just going to do heap queue.heap push self.heap and node, right? I'll push the node into it, and I have to do self.cache, right? Self.cache key equals node, and record the node. Okay, so I spelled it wrong. So that shall be it. If it's smaller, right? We'll just push it in, and then heap push already will reorder everything, so that's not a big issue. Else, right? Else means the heap is of the size of the capacity. So if the heap is of the size of the capacity, then we have to remove something and hopefully guarantee that the front of the queue is always bad. So we need to say node to remove, right, shall equal to, let's say, heap queue dot heap pop. Pop self.heap, right? So we pop it out. So that's the least recently used. So we pop it out, and I want to, so not only pop it out, and delete it as well. So I say delete self.cache node to remove.key, right? So we'll delete this. So this thing is completely removed. And then I will do node. So now I realized this one is a common step that all of them have to take, which just means we do the equal and equal, and like this. Right? If it's equal, then I need to delete something first, and then I add a new using the current. That's actually not true. I just realized something. Oh my god. If the key is in cache, I forgot this step. If the key is in the cache, right, then all we do is self.cache key, that's the node.val, what equals to the new value, so we're updating the value, and we have to cache key, right, dot frequency, need to plus equal 1 because I use them more frequently, and self.cache key, last one's the tick, need to equal to current tick. And after that, we're gonna do heap q dot heapify, right? I have to heapify self.heap. As I update it, I have to do this. Else, if it's not in it, right? If it's not in it, then we say if the length is equal to, then we need to pop some stuff, and then we guarantee that the top is always the least frequently used or the least recently used. So I pop it, I remove it, everything's fine, and I add a new one, which is good. And a heap push also does the reordering as well. So set to, yeah, so that I think is the put. Now we're gonna handle the get, right? So the get, of course, if key is not in self.cache, right? We simply return, what do we return? Return -1. So we just return -1. Nothing changes, right? So if key is in the cache, right? If it's in the cache, then we're gonna do the same thing here. We're gonna do, oh my god, our cat just went crazy. What did you find, Jimbo? He's panting. Alright, so we don't have to update value, but we have to update frequency. Do we have to update a tick? Yes, because it's used. Every time you use, frequency changes and your tick changes. So we do all these, but when we have to reorder. We have to do this. No, not this. We have to do this. Yeah, this just means, and then we return self.cache key dot value. All right. So the only worry is every time now I have a login. I will just see how many times I will do call. 2 times 10 to the 5th call. Jeez, and each time it's going to be login capacity 10 to the 4th. All right, let's see. Let's see if it works. Yeah, I'm not going to test this one, so I just comment it out. Oof. All right, let's run it and see if it's correct. All right, seems to be correct in this one. I'll just go for it. There's no way I can know, right? I think runtime error. What the heck is this? Index out of range. Oh, nothing to pop. Hold up. What? What does this mean? Capacity can be 0. You gotta be kidding me. Capacity can be 0. Well. What do I do if capacity is 0? So when you put, we do this, key is not in, and I check if it's equal to capacity, and I want to pop. But yeah, I cannot pop because there's nothing in it. So that's a special case. Capacity is 0. Because this, we always think we have capacity. If it's 1, then we can always add a node to it. But capacity 0 is just cannot do. Okay. Okay, we'll just say if self.cap is equal to 0, then we just return. There's no way I can handle this. It's a good test case. I didn't realize. Didn't read the problem carefully. All right, let's try this one. Last time I do this, I had like 5 or 6 wrongs. Oh, we might either wrong or we time out. Darn. They don't allow you to use this, right? I think it's probably timing out. Oh, that's why it's a difficult question, man. Oh my god, look at this. Oh, jeez. Okay, so this data structure is not working. I mean, it is working, but not working with this. How many we pass? 22 out of 25. Okay, this is TLE. Now we gotta think. Right? Now we gotta think. Okay, so O log n is not good. Okay, that's fine. Let's redesign. Doubly linked list, right? Let's go back to doubly linked list and see if we can, do some magic about a doubly linked list. So a doubly linked list, I am able to determine. I'm able to determine the frequency, not frequency, when they're used. If I use a new one, I simply put that to the end. So the front is always the oldest one. Okay, that's fine. How about frequency, right? If I use one, I also throw it to the end. Huh? Maybe, yeah. Hold on. The least frequently used, right? So, but how do you know it's least frequently used? Yeah, that's the problem. How do you know? Least frequently used, which is how many times this one has been used. Least frequently used. 10 to the 4th, right? Log n. is we have to find an O1, O1, I was to say O1, O1 for get, O1 for put. So we have to figure out a smart way to handle the frequency. Frequency. How do I handle frequency? I'd say if I have a linked list and it's linked by frequency, okay? It's linked by frequency. It's linked by frequency. What do you mean by linked by frequency? Say, first use the frequency is 1, and next time use again as a new node, but it's not, it's most recently used, so come here, okay. Then I use 1 again. Okay, then use 1 again. Then it has a maximum frequency, so I put at the end. How do you know where to put? Yeah, that's the problem. How do you know where to put the node? Yeah, so like if you use a node again, so it's recently used, but its frequency is low, so you take it out, but you have no clue where to put it. All right, you have no clue where to put it. What if we have a hash map with the key being the frequency? Okay? With the key being the frequency, you can't. If the key being the frequency, you want to find the smallest, I'll take ON. But that's depending on how many different frequencies we have. Right? That's how many different frequencies. Maybe it could be, but it's all log n. 10 to the 4th. Log n is 4. Okay? That's technically it's not 4 because log n is log to the base of 2. So what if we don't have a lot of frequency? If I use it, right, that's frequency 1, and a new one has frequency 2. So within each frequency is a linked list. How about that? Within each frequency is a doubly linked list. Oh my god. You gotta be kidding me. Within each frequency, that's a doubly linked list. Whew. Okay, within each frequency is a doubly linked list. And the frequency is the key of the hash map. Okay, so when we get the cache, we'll always cache on the node. So we grab the node, and we also know the frequency, so we put the frequency as well. And we go to the hash map. So the get call, okay, the get call, because it's a double linked list, we don't need a tick, right? There's no need for the tick because the tick can be handled by the double linked list. So within each frequency, we use the same LRU cache. It's LRU cache for each frequency. So we'll get the node, we will get the frequency, so we can find the linked list, and we do whatever operation we need to do with that frequency. Well, of course, if I use it, right? If I use it, then the frequency changes, right? If I use it, the frequency increases. So I have to remove from that W linked list and push into a different W link. I can't even talk. To push into a different doubly linked list of that frequency, right? And then if it is at capacity, then we find the smallest. How do we find the smallest doubly linked list? I mean, we can keep, in this case, we can keep a heap. All right, we can keep a heap, but just we don't have to call heap every single time. We keep a heap, and we look at the node, we look at the front, right? That's the frequency, and then we just pop the front. And after pop, we ask the question, the length. What's the length of? If the length becomes 0, then we pop on that, right? We pop the thing. We pop the frequency. So the frequencies will be, there will be no, like, say, frequency 1. It doesn't exist anymore. But then I add a new one. Okay, so let's try this one. Oh, this one's going to be, madre mia. Now I understand. Well, the reason I want to do this problem is because I saw some person mention that, oh, you think some problem is complicated, try LFU. And then some people are like, yeah, I tried it wasted me 2 hours and I got like 200 lines. Now I know what they're talking about. Can I reset to default? How? This one. Yeah, I reset to default. Again. Okay, so attempt number 2. To simplify it, what I think I need is double DL node, double linked list node. Okay, so I have a DL node, which I'll just copy this. Right, DL node object. All right. So what is this? I need a key value. I don't need tick. Okay, I just need the key and I need the value. And key value is no frequency, but we have to have pre, right? And next. Okay, pre, that's the DL node. And then I have to create a new one called class double linked list. That's an actual double linked list. And what do we need for this? Well, we don't have to do anything actually for the initiation, but I do need to have a self.length is 0, right? And self.length, self.head is going to be a D node, and we can just -1, value is -1. Let's make sure that these values will not be set. Key is $0. Yeah, we just that's fine. So that's the head and self.tail, head and tail, right? And everything will be inserted between them. That was the trick. Self.head.next equals self.tail, and self.tail.pre equals self.head, right? So that's initializing. Then we're gonna say add, right? A node, and this node is going to be a DL node. I'm not gonna return anything. Okay, so how do we add? We always add the tail. So what we say is the tail, tail, self.tail.pre. Oh my goodness, self.tail, dot pre, dot next equals node, okay? And node dot pre equals self dot tail dot pre. So node dot pre equals self dot tail dot pre. Okay, so we handle the pre. Now we say self dot node, not self dot node, self dot tail dot pre equals node. All right, and node dot next equals self dot tail. We handle everything. Pre dot next, right? Node dot pre, node dot next, and self dot tail dot pre. Yeah, that's it. That's add. Def remove. That's called pop. Always pop front. Yeah, I want to return the DL node, return a node. Okay. So we always pop the front, which means node will equal to self.head.next. Right? Oh, my bad. One more thing. Self.length plus equal 1. And if self.length is equal to 0, return none. Then we have to be optional. Otherwise, node.self, this is a node to be returned, and then we say self.head.next equals node.next, right? This one dot next equals node.next, and node.next.pre equals self.head. So head.next we handled, and node.next. So node is still pointing, right? Node.next is still pointing, and node.pre is still pointing, but that's fine. So we're not using the node anymore, but we can just say node.pre equals node.next. None, just to remove all possibility of contamination. And we return node. That's pop. Okay, that's double linked list. Okay, now the fun just began. All right, we have capacity, self dot, and we have a cache to allow us to know where the node is. What else? What else do we need to know? We need to know. We need a hash map, right? We need a hash map. Now, the hash map is going to be. How about we set the hash map to a default dict. Can we set a default dict? Yeah, I think we can set a default dict. Let's try default dict. Just be fun. Let's have fun. From collections port default dict. Okay, let's have some fun. Default dict. So this I say is going to be a default dict of double linked list. How about that? Okay. So I have capacity. I have cache. I have hash map. Actually, let's not call it. Let's call it frequency map. All right. What else do I need? That's it. That's all we need. Okay. Get. Very easier to write. We want to get So we, again, if it's not in, if key is not in cache, we are returning -1. Easy peasy. Okay. Otherwise, if it's a key inside, right? If the key is inside, what do we do? Well, if the key is inside, what we need to do is, of course, find the node, self.cache key. Okay. So now we find the node. Now what? Well, we find the node. Now we need to remove it from its frequency. Do you know its frequency? You don't know. Why? Because you stupid forgot to include frequency. I said frequency is needed. Okay? Frequency is needed. So now you grab the node, so you notice frequency. So now you need to remove it from, okay? So what do we do? Actually, this is not right. I just remember, this is not right. It has to be removed. It has to be a node. Oh Lord. The DL node was that as a should be removing a node that you want, which is true. That's what double linked list can do. If it's equal to 0, you say you cannot remove anything. Which actually it's, yeah, you shouldn't have that. But, let's do this. Assert. When you call remove, then the length must be larger equal to 0. Otherwise, you cannot call remove. Let's do that. And it's not necessary. I already know the node. So I just say head next equals to node.next. Node.next of 3 equals this. And I clean out the node. Okay, so that's remove. Remove the target node. So I got the node, right? Then what do we do? I have to remove it. Right? I have to remove it. How do I remove it? I say node.frequency. Right? Node.frequency, I can get it from self.frequency map, freq map, this frequency. This is a linked list. Dot remove node. Okay, so the linked list, I remove the node, and then node.freq plus equal 1, increasing its frequency, and then I'm going to add it to, then I need to add it to self.frequency map, node.frequency dot add node. Booyah! That's it. Oh, and return. I didn't return a node.val. Booyah! That is the get. How about put? Well, to do put, I will do this after I take a leave for a very important thing. Alright, I'm back. And while I was away, I realized one thing. We need a heap to find the smallest frequency. Okay. Okay, so now I just realized this might not be the best idea because I do have to check, right? When I get it, I don't have to check. But if the frequency, you know what? Because I need to check. There's no point of doing this. Let's do it that way. All right, and then, okay. Yeah, so I get it, I'll remove it. Then we need to check. Now how do I remove it from the heap? Thought about that? How do I remove it from the heap? Exactly. Okay. You can't. Yeah, like this frequency doesn't exist anymore. You know what? Let's try not doing this. But we do have to remove. Right, notice this. Remove. We say if self dot frequency map dot frequency dot length is equal to 0. Right? If the length is 0. Oh, I forgot the length. My bad. I have to do the length. So we say if the length is 0, then we just say del self dot frequency map dot frequency. Okay? Frequency plus 1 if dot frequency is not in self dot frequency map dot frequency equals a doubly linked list. And then we add. Right? There's no longer we have the frequency for this. Because I increment on the frequency. And we always add to the end. Okay, now we do put. Okay, so again, if self.cap is equal to 0. Do we have to if we do it this way? Let's try now. Let's just say if key is in self.cache, right? So key is inside, so we're just updating it. Right? If key is inside, we're just updating it. Now updating is the same thing. I have to go through the entire thing. If you think about it, right? We have to do the entire thing. Because if it's in it, I put value in. It's just like I need to get it. I need to do all this. So which means, say if self.get the key, right? If I get the key is smaller than 0, right? If it's smaller than 0, that means it does not exist, right? So we do some stuff. Else, that means it does exist. And I already increment the frequency, and I have this value, but that's fine. It doesn't matter. Right? It doesn't matter. What we know is its frequency has changed, right? But it's fine. So all we need to do is just update its value because its position has already been updated. So we just say self.cache key, right? .val equals value. That's it. That's all we need because we have already done all the move around. Yeah, we get it first. We do the remove, we do the add, and when we remove, always, now this is just remove the node, right? It's different. And now, if it's smaller than 0, which means it does not exist in the cache, right? So it's not in cache. So if it's not in cache, and then we need to check, right? If capacity, if self.cap is larger than 0, so we have capacity, so we just add, right? So we create if it's equal to 0, right? Because we check equal to 0 first. We see here, then we remove first, right? So now we do remove, okay? We do remove a node. Which node to remove? So we need to first find the min frequency is equal to min self dot frequency map. So this, I hope this doesn't take too long, okay? So I will get the minimum frequency, and then I say self dot freq map, right? Minimum frequency, still linked list dot remove something. Remove what? Self dot do I need to know the node? Don't have to. I do need. So node to remove will equal to self dot. My God. So it's this thing, right? Self dot frequency map minimum frequency linked list dot head dot next. All right, that's the one. That's the one to remove. So now what we're gonna say is dot remove node to remove. Right? Okay, so I remove it. Everything's fine. But the same thing, right? If this minimum frequency, if the length minimum frequency is 0, I will remove it. Remove from the frequency map. Hold on. Okay, and I remove it from the frequency map. So that's done. And then node to remove is removed, right? From the frequency. And then what? Then I need to see and remove its key. So I can say del self dot cache node to remove dot key, right? And to remove its key as well. This is if capacity is 0, I need to remove the minimum frequency with the least recently used. Okay, so this is all done, and then I need to add a new one, right? And capacity equals to 0, I do this, and then self.cap plus equals 0, capacity goes up. And now I need to add a new one. So I'm going to create a node, right, equal to DL node. What DL node requires? Key and value. So key equals key, val equals value, right? So I create a node. and its frequency is 1, right? And then I create this node. Then what? Then we want to self.cap minus equal 1 capacity, right? And before we do that, so I create a node, so I need to self.cache node.key, just key, right, equals node. That's also fine. Before doing that, now I have to do the cache, do the frequency map thing. So we say if node.frequency is not in self.frequency map, right? Then self dot this one node.frequency, which is just 1, right? If you think about it, it's just 1, but it's fine. Equals a double linked list. Right? And then self.frequency map. Oh yeah, let's just do 1. We know this is a 1. Because we're trying to put node into it. This is the frequency of the 1. It's not in there, right? So we say frequency map 1 dot add node. Alright. We're going to try. Invalid syntax. Line 26. It is invalid. Argument function is, oh my god, self. Just syntax error. Minimum argument is the, where? Line 56. Ah. Oh, so let's just say if self.cap. Holy guacamole. Can't do that. If self.capacity is 0, and then if nothing is in the frequency map, okay, so that's the thing. If a equals to 0, and now we do a bunch of stuff we want to pop. But if there's nothing in frequency map, there's nothing to pop. And there's nothing to add because I can the self.cap. Which made me think I need to have self.length, right? Equals 0. Get, fine. Yeah, it didn't change. When you get, it didn't change anything. When you put, right, if key is smaller than 0, otherwise we don't change the length. And then we can do here, if self.cap is equal to 0, then we just return. Don't do anything. And this is if self.length is equal to self.cap, right? Then we do blah, 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 and then we don't do self.cap dot plus 1. This is self.length. If the length is equal to, then I just don't change the length, right? there's no change. If that's equal to, I remove it. Yeah, I have to change self length, right? Length minus equal 1 because I pop 1. I get a new one. If I say if 1 is not in, create a new one, and blah, blah, and this is plus equal 1. We do self dot length. Okay, this can solve that problem. Okay, so this is right. Now we're gonna come here. Oh my god. I don't know how long this one is gonna be. So it all depending on the frequency. Right? How many different frequencies can we have? None type has no pre. Okay, that doesn't look nice. That shouldn't happen. When you remove, right? If I have a add, right? We always add tail dot, hold on, let me think about it again. This is the tail. Tail dot pre dot next equals node. Node dot pre equals self dot tail dot pre. So it's connecting here, connecting here. And then self dot tail dot pre equals node dot next equals to tail. So self dot tail always points to the end. In order to remove the node, right? The node could be anywhere. Oh, that is not correct. That is not correct. When you remove a node, it shall be node, my bad, node.pre, node.pre.next equals node.next. Node.next.pre equals, hold on. Node.pre.next equals node.next. That's true. And node.next.pre equals node.pre. Try this one. Yeah, because it's not pop. It shouldn't involve self.head. All right. It looks promising. Let's do this. Come on. Yes. 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 Let's go, baby. Let's go. So the idea was correct. So this is 01, right? This is 01. We know that. This is 01. Because there's nothing special about it. Everything's 01. This depends on this. This is the only not 01 operation. So to make it fast, we just need to know the frequency map, right? But we know the frequency map, all right? So like because each node can only have one frequency, and because I remove if the frequency is gone, so it won't have. If I have a large frequency, and every time I add a new one, it'll always be frequency 1. Every time I go to that frequency, it will be 2. And when the frequency is 3, this will be removed to 3. So the ideal is no matter, like if we go random calls into all this, then the frequency of each one, like if we call one a lot of times, and then we'll just add and remove, right? So there won't be a long consecutive array of numbers. That's the idea. It won't happen. Like for node 1 is frequency 1, node 2 is frequency 2, node 3 is frequency 3, node 4. I mean, technically I can create, or just create and put, and then we have 4, and then we do 1, 5. So it is possible to create such a thing, but yeah, so I guess. Well, anyway, so let's summarize in this one. We create, so the key for this solution is to create a frequency hash map where freak map, right? Where freak map f is a doubly linked list that contains nodes of frequency f. The doubly linked list is used to handle the LRU cache, right? When the frequency is the same, and the freak map is used to obtain the smallest frequency by finding the min of its keys, right? Finding the min of its keys. As long as the operation is not designed to create a long list of distinct frequencies, it is not likely that there are a lot of keys in freak map. But get is always O1. Put is ON, depending on the different frequencies currently present. Let's run as 1095.66. I mean, the solving the LRU cache definitely helped with this. All right, let's see. What do the smart people say? 2 dict plus, yeah, we do have 2 dict. Double linked list. LFU cache. Oh my goodness. All right, I need to read this one more carefully. I think it's probably a different data structure compared to mine. An order dict. I think this is a linked list. This is double linked list. And a cache. Node. Frequency, yes. A min frequency. How are you updating the min frequency though? Double linked list. Frequency, the first one. Sentinel doesn't matter. I have a different way to do this. Frequency. Yeah, I do have the frequency because I needed to know which this one it belongs to. How do you update the min frequency though? Yeah. I insert in the tail, same thing. All right, how do you do that? How do you maintain the main frequency? Update the node's frequency, append to the new if the is empty and self dot main frequency equals f, update this to f plus 1. Yeah, this is the part I don't understand. So what we need to do is, I don't have to check this, I need to check the cache, update. Append a node to new, if old has size 0 and chef main is f, update it to f plus 1. Okay, so this is the key. If old has size 0 and self dot. All right, so we have this, right? So we have this minimum. So we have some minimum. If we pop this and we find out that the D-linked list has size 0, so which means this one has to be popped. And the minimum frequency happens to be the same, right? Happens to be the same. And then we say we need to update because the F frequency doesn't exist anymore. So I need to update this plus 1 because F plus 1, it does exist. Huh. That does make sense. That does make sense. I can reset to 1. It doesn't really matter because for each node, the frequency has to go through 1, 2, 3, 4, 5, right? So if I align my minimum frequency, and then if anything changes to the node in that minimum frequency, well, I mean, it's either if you pop, what if I pop and nothing new gets put in? Hold on, like if I pop and put it into a new frequency, then it can resolve, right? If it's pointing the same, which means it doesn't have, then go move on. That's fine. So if I pop is because capacity issue, and nothing new is coming in for this frequency, right? So I pop, and it's nothing. Then we add a new one. Oh wow, wow, that was good. That was very good. That was very good. Very smart way to maintain minimum frequency in O1. I don't think these people can see this anymore, but that's fine. Update. This solution uses a very smart way to maintain minimum frequency in O1. The trick is to realize that when a new node is added, minimum min frequency is always set to 1. When a node is popped from a frequency, if there are still nodes left, we don't have to change minimum frequency. If there are no node left in that frequency and it is not the same as min frequency, we don't have to change min frequency. If the if it is the same as min frequency, right? If it's the same as min frequency, it is guaranteed that this type of popping will result in the popped node to be inserted into the linked list marked with frequency +1. So simply update minimum frequency to +1. Right, so that is, so basically we're going to do self.frequency, min frequency, right, or equal to 0. So I want you to get, right, we need to get. So I say if equal to 0, then I'm going to pop. Now here is the thing, right, here is the thing. We say if it is 0, right, now we pop, and we say if node.frequency, that's the one to pop, is equal to self.min frequency, then self.min frequency plus 1, and then to match, right, that's fine. And for here, I'll get key, so we handle everything. And then if it is equal, then I'm going to pop, but it's fine, we don't have to change the frequency, right, we don't have to change anything, right? We don't have to change anything, because I'm going to add a new one, and I say node equals blah, 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 and self.min frequency will equal to 1, right? And here, I don't have to do this, okay? And then all of this, will be self.min frequency, right? Because it doesn't change, we just get a min frequency, and I can remove it, which is fine, right? I say if min frequency is 0, I remove. I don't have to worry about min frequency, because I know in this situation, I will always add a new node, and the min frequency was set to 1. Therefore, we need to check this code as well. Okay. Add this one as well. So a very comprehensive example. All right, let's see. DL node is not defined. Of course, it's not defined because I didn't put any of the other node into it. Not this one. But I am happy that we did hit the right solution. We had the right idea, correct idea. And there we go. All right, let's try this one and see how fast. I don't think this can be any faster. Maybe it can be faster. That's fine. It's fine. But we know. This is the update. 01. Everything is 01. 01. This one is 01. Very good. Very good. Very, very good. Alright, that will be it. I'll see you guys very soon. Adios.